Hello and welcome to our webinar today. Today we will be talking about AC and DC protection for Fronius inverters. And joining me today is my colleague Byron Kotze. He is the TSA or the Technical Sales Advisor for Southern African region. He's based in Joburg, South Africa. And myself, David Mwangi, the TSA for the Eastern African region. I'm based in Nairobi, Kenya. Today, we will talk about generally the various protection classes. We will talk about DC isolation, the DC switch, Fronius solutions, and retrofitting, lightning protection for PV systems. We will also talk about reverse current, string fuses, reverse polarity of strings, AC grid and grid system protection. We will talk about how grid system protection works for Fronius inverters and the installation of that. And after that, we will also provide you with some additional information. So like usual, if you have any questions, please feel free to post them in the questions area of the webinar, and we will do our best to answer your questions as we go along. And also, we appreciate your feedback. If there's something specific you would like to inform us about any webinar or any topics that you would like to be covered in future, please feel free also to let us know. So let's get started and talk about protection classes. So there are basically three protection classes that deal with various types of protection and different areas. So we have class 1 that addresses grounded circuits. We have class 2 that is related to double insulated circuits. We also have class 3 that is related to extra low voltage circuits. So these protection classes are applied for both AC and DC systems. And for grid connected PV systems, protection class 1 and 2 are actually enough. Looking at protection class 1, the idea is actually to provide fault protection, whereby the following measures are taken. So we have number 1, single isolation of cables or circuits, and then the grounding of metallic parts or the chassis of a particular gadget in combination with overvoltage current or residual current devices. So this small picture here basically shows us, or diagram here shows us how this setup would look like. So you would normally position an overcurrent or a residual current device in a chosen position, and then this will be able to divert any fault currents that would arise. Looking at protection class 3, this is to provide adequate fault protection, whereby this would address then double or reinforced insulation of cables or circuits. And in addition, other measures are taken to ensure that for parts of a system that are exposed to harsh environmental conditions, such as heat, ice, or UV rays, for example, cables and stuff like that, you do not have premature failure or breakage of these cables. So we have, in addition to that, also the isolation monitoring for a transformerless inverter, as well as the residual current monitoring also that is designed within the transformerless inverters. So in this case, we can see an example here. So the highlight here is to show you that, for instance, there are some extra measures that are taken for PV cables to make sure that they can withstand the UV rays and other environmental conditions. So the design and construction of a professional PV cable is actually quite different from other cables that are used for maybe AC power transportation. So looking at the DC isolation, and this is actually for protection class 1 systems. So in class 1 systems, one of the following measures is actually used. So you have the possibility to use the GFDI, which is the ground fault detector interrupter, or go the route of impedance grounding. So talking about the GFDI, this can be realized in different ways. And it's quite common actually to use a DC fuse in the range of 1 to 3 amps. And this depends on the size of the system in question. And then the protection function is that if a ground fault occurs, then the fuse or the current monitoring device opens the connection, as we can see here, to the ground, so that the fault currents are diverted, and therefore you are able to protect that particular device. However, GFDI has some non-detection zones, so and therefore it's not suitable for protection of humans, because you could have current up to 1 ampere passing through as a fault current, and 1 ampere is actually too high for a human being to be exposed to. So if the fault occurs, as an example, also through the earth conductor, then it will not be recognized, and another fault results in a hazard. So the remedy for these two kind of shortcomings for GFDI would be to use a class 2 protection scheme, whereby the GFDI is then able to disconnect the ground connector before the start of the operation. And then this must be able to detect if there is a ground fault in the grounded part of the system. When looking at the impedance grounding, so in this case, the system is grounded by a high impedance, which limits the fault current to a certain less dangerous protection limit. So a typical value for this less dangerous current is about 30 milliamperes. And therefore, if you consider this as the maximum fault current that you want whenever there is a trigger for failure, then for a system that is about 900 volts, then your typical resistance would be in the range of 30 kilo ohms. And this is quite common, for instance, for RCDs or the residual current devices. So you can see here the scheme of the impedance grounding, how this would work, so that this fault current then would trigger the RCD to disconnect the system from the power source or the error source. So let's now talk about class 2 protection systems. And in this case, we address it in two categories. So we have the transformer-based inverters, whereby the inverter in this case measures the impedance to ground from the positive to the negative connection via the impedance network. And if this impedance value decreases to a value below 100 kilo ohms, then a warning is displayed. So in this case, the system does not necessarily disconnect from the system, but a warning is displayed. On the other hand, for transformerless inverters, the inverter then measures the impedance to ground between positive and negative before start of production. So, and this would typically happen every morning before the inverter starts producing or injecting power to the grid. And during the operation also, other protection measures are also integrated. And one of these is the RCMU, which is the residual current monitoring unit, which detects residues of current that would actually jump from the DC to the AC side of the inverter. And we have, if you have in excess of 300 milliamperes through the RCMU, or this value rapidly changes by 30 milliamperes, then the inverter switches off, which is a big contrast to a transformer-based inverter. So this particular function of checking these variations of the fault currents in this range cannot be used or cannot be achieved by commercially available RCD devices or residual current devices because these units are not able to detect these sudden jumps that would trigger an off signal for the inverter. Let's now talk about the DC switch and the requirements. So we have DC isolation requirements according to IEC 60364-7-712. And this requires that there must be a means to isolate on the DC side of the inverter. And this is actually a standard across many parts of the world. So the requirement, therefore, is that if you have to do some maintenance work on the inverter, you need a means to isolate the inverter from the DC source. So this is achieved using the DC switch. And then in addition to that, the DC disconnector or the DC switch must be able to take the full power that is coming from the DC side, as well as withstand the maximum voltage that is flowing from the DC side. It's also possible to do a combination between switching, that is by a switch, and also complete isolation by way of DC plugs or the MC4 plug. So if you have MC4 plugs and you want to totally isolate the DC connection to the inverter, this can be achieved by the MC4 plugs. So having said all that, let's briefly talk about the available Fronius solutions and how you retrofit them. So starting off with the snap inverters, we have two possibilities. So we have the solution for the small inverters up to 8.2 kilowatts, and these are available as DC surge arresters type 1 and 2 only, and this is the M version, meaning that this surge arrestor can be connected to the two MPPTs within the inverter, and this is actually only available as a retrofit kit, means that you cannot order the small inverters up to 8.2 kilowatts, and here you have to align the snap inverters with the SPD integrated from the factory. So this means that once you order the inverter, you would need actually to fit it on your own, and some hardware adaptations may be required within the inverter for you to be able to fit the SPD, as you can see it to the left here of the photo. In addition to that, for snap inverters as well, we have a solution for the big snap inverters, and this means that inverters above 10 kilowatts. And this, we have 4 technical designs for DC surge arresters. So we have the type 1+2 for a single MPPT or multiple MPPTs, and we also have the possibility to get type 2 surge arrestor, both single and multi MPPT. So here you can see that you get a bit of flexibility for the bigger snap inverters, whereby you can choose, depending on the level of protection you perceive for your inverter or the particular system, to order either type 1+2 or type 2 only. So it can be done as a retrofit kit. So it's possible also, if you do not have this already retrofitted within the inverter or fitted within the inverter from the factory, you can order the SPDs and fit it within the inverter. So all that is needed is a DIN rail. As you can see, the bottom right here, we have a DIN rail where that is holding the SPD, and then installation ex factory in this case is possible. So this is a contrast to the smaller inverters where I said installation of the SPDs from the factory is not possible. We also have a solution for the Fronius Gen 24 Plus inverter. So this is offered as a DC SPD type 1+2. So this is also similar to the snap inverter, the small snap inverters up to 8.2 kilowatts. This is also a retrofit kit. And you can see here that the SPD is mounted on a print board that you actually need to fit on your own when you are working on the inverter. And you have the connection to be done on the DC side of the inverter. So no ex-factory fitting of this SPD is possible. And if you have ordered a Gen 24 Plus inverter without the SPDs, then you can order through the normal distribution channels and you'll be able to get the right SPD for that particular inverter. Let's now talk about lightning protection for PV systems. So such damages to PV systems are caused by, among other things, by lightning. So therefore, surges pose a serious threat for PV systems damage. And here we are talking about the effect of transient surges in the microsecond time frame. So these surges can be a result of lightning discharge. It can also be a result of electrostatic discharge or switching operations. These switching operations can also mean that where the particular inverter or PV system is operating, you have some heavy machinery that once they are switched off, they actually cause some surges of current to flow back within the network, and this can actually also become problematic for both inverters and other electronic devices within the installation. So the kind of damages that can result from this kind of surges can affect both the hardware and software sections of the inverter, but ultimately this can also lead to a total failure of that particular component. So when you talk about the various causes of damage to PV systems, we can see here the pie chart that has allocated the probability or the percentages that would relate to each of these particular error causes or failure causes. So we can see that surges account for about 18% of the failure occurrences. And we have other things like snow pressure, storms, and as well as fires. And this data is actually from photovoltaic.eu. So this is something that has been studied for quite some time. So you can see that this 18% is actually quite a significant possibility that, depending on the location, because the location is also very important, surges from these causes that I've mentioned here, lightning discharge especially, can be a significant factor to consider when you are installing your PV system. When it comes to the danger posed by lightning strikes, we have to look at the lightning density. And in this case, we are talking about the strikes from cloud to ground, which is abbreviated here by NG. And then we look at the lightning strikes per kilometer squared per year. So on average, there are about 6,000 lightning strikes on Earth every minute. So that's quite a big number. And you can be able to tell what is the likelihood of a lightning strike in a particular area by, for instance, looking at the NG chart. So you can see the NG chart here to the right. And if you are somewhere, for instance, in Central Africa, so you can see actually quite a big portion of the African region has a big probability for a lightning strike at any one particular moment. So as an example, in a place called Kifuka, this is somewhere in Congo, Central Africa, there are about 154 lightning strikes per square kilometer per year. So that's really a very big number. And each of these strikes is actually a potential risk for damage for electronic equipment, including your PV system. And therefore, mitigating measures for this kind of strikes, depending on which area you are going to do your installation, are important to consider. In the case of lightning strike, what happens? So we have these transient surges, and these are not foreseeable. These are not like the normal periodic voltages or currents or loads that you can expect within a network. These surges just come out of nowhere. And in terms of the lightning itself, the strike itself, we can classify it into a leader charge. And then the combination of a leader charge and a catch-up charge will then build up the main lightning discharge. So therefore, out of this, you can get what we refer to as the impulse currents that happen within very, very small durations of time. And then you have the long time currents. So these long time currents would actually be the biggest cause of damages or even fires. So you can see that these long time currents are actually within a fraction of a second, but because of the magnitude of the current that is flowing, then you have a very high probability of failure the longer it takes for the lightning to fully discharge. So the impulse currents are not really that problematic, but once you have the discharge going on for 0.2, 0.3 seconds, then that becomes a big concern for worry as far as damage to electric or electronic equipment is concerned. So when it comes to surges on the AC side of an inverter, the most probable thing that is going to happen is that when there is an AC surge, the varistors on the AC side of the inverter are going to be affected, and this can actually be the result of an indirect lightning strike. It could also mean that these are coming from due to a bad or missing connection to the neutral conductor or cable. And then also surges of the AC grid. There could be quite a number of causes for this. Like I mentioned earlier, it could be that you have some very heavy loads, maybe big loads with motors, and once they are switched off, they produce some backflow of current that can create some surges within the network. So we have different protection systems for AC surges. So you actually would have quite a number of things or solutions to choose from, but the intention there would be to arrest these surges. So some of these solutions on top of the regular SPDs that would trip can include more advanced systems such as the automatic voltage switchers or even automatic voltage regulators that are microprocessor based controlled, and therefore the regulation is actually much better than just a typical SPD. The important thing to note here is that if an inverter is damaged as a result of a surge on the AC side, then that does not qualify as a warranty case. And therefore, it is important to ensure that whenever you install Fronius inverters, you take adequate measures to ensure that on top of protecting the DC side of the inverter, the AC side is also accordingly protected. And actually, if you consider the AVS and the AVRs, they actually give you some better possibilities, because with the same components, you can actually protect the entire premises, not only the inverter, whereas an SPD most likely will only be protecting the inverter. So therefore, the question is, how can you optimally protect a PV system? We have several things that we can observe. One of these things is related to grounding and potential equalization. So when there is proper grounding and potential equalization, then this forms the basis of each surge protection system. And then it is important to ensure that the grounding resistance is kept as low as possible. And in this case, we are talking about a value that is less than 10 ohms. When it comes to cabling and routing of cables, here it is important to ensure that you follow proper cable routing procedures. And some of the best practices is when you're doing an installation with quite a number of cables that need to be installed, you use cable trays so that these cables can actually be properly arranged. And then you keep conductor loops as small as possible. And in addition to that, you need to separate protected and unprotected cables. In terms of lightning protection, depending on the area and the lightning intensity or density that you expect in that particular area, you have to consider an interception system and an arresting system for the lightning. So you can also have integration of a PV system as a consideration for the overall lightning protection concept. And if this is a normative requirement that by law you are required to do a lightning protection system when you do a PV system, then this is something that you already have to consider in advance. When it comes to professional application of lightning protection systems, there are actually some trained experts who deal with this kind of solutions. And therefore, if you need this kind of advanced solutions, it's always good to get in touch with the professional lightning protection experts. For internal lightning protection, the most important thing is to ensure that you have potential equalization in addition to surge protection devices, and then look at which surge protection device topology fits best to that particular application. And this can be integrated, as we have seen for Fronius inverters. So in terms of which factors need to be considered for overall protection, we can talk about internal lightning protection. If you want to minimize the probability of a fault or a default in the system, if you have an issue to deal with insurance, and therefore this relates to regulation, and maybe you get even higher premiums from the insurance providers if you do not have proper protection of the system. And like we said, for Fronius inverters, you can simply do very quick retrofitting, especially on the DC side, and you're able to protect the inverter. And yeah, overvoltage protection would actually offer you maximum safety within the network. So for the various topologies of SPDs, there are typically 3 classes that are used. So we have type 1+2, which is a combination arrestor, and it is able to protect both the faults within the coarse and middle range. And this, in addition to just being an SPD, also does arrest lightning currents. So the most typical point of installation is after the energy meter or at the feeding point. This is for the AC side, but of course for the DC side, this is integrated within the inverter. And then for type 1+2, the residual voltage in the range of 1,300 to a maximum of 6,000 volts. Then we have the next topology is type 2. This is basically a surge arrestor. This offers middle protection, and the residual voltage is in the range 600 to a maximum of 2,000 volts. We also have type 3 that offers fine protection of electronic devices. It is able to effectively eliminate small surges. This can be done in-house. And if you combine the type 3 plus either type 1+2 or type 2, then you are able to offer even better protection that would be a source of damage from bigger surges. For overvoltage categories, it's important not to confuse them with overvoltage protection. So in terms of overvoltage categories, we have 4 categories. So we have category 1, 2, 3, and 4. And the differentiation here is by the peak voltage strength. And the classification therefore depends on the materials that are in use, as well as the insulation resistance and the type of network link, meaning where this particular overvoltage is actually connected. So when it comes to the various limits, we have category 1 up to 1,000 volts, and this would be something that would be applicable for laptops and phones. We have category 2 that goes up to 2,500 volts for household appliances, and then category 3 maximum 4,000 volts. This is for fixed installations and continuous connection systems. And then you have category 4 for systems up to 6,000 volts. And this would be like for a connection point of installation, maybe the grid meter or something like that. So when it comes to the Fronius inverters, these are protected through the overvoltage category 2 and 3, both on the DC and the AC side of the inverter. Let's now quickly look at the reverse currents. So reverse currents are also a bit of a problem within PV systems. And if you look at the characteristic PV or IV curve, the reverse current operation, as we can see here, it can be a reverse voltage or a reverse current, then behaves as a consumer instead of producing power within this range. So the typical causes of reverse currents can be parallel strings with different open circuit voltages. And fault examples could be a short circuit in one or more modules. It could also come from a short circuit in one or more cells within a module. It can be a double ground fault in a module or somewhere in the cabling of your system. And the consequences would mean that most likely these reverse currents over a period of time can actually destroy the PV modules by creation of things like hotspots within the PV array. So this is the typical reverse current operation. So most modules are rated generally for a reverse current of about 2 times this short circuit current, but mostly also in the range of 1 by short circuit current, maximum of 3. But further analysis done by Fraunhofer, for instance, reveals that even 7 times the rated short circuit current for about 1 hour does not show damage to the PV array, but it's always a very good idea to make sure that your PV array has adequate protection against reverse currents. So now at this point, I would like to hand over to Byron to take over and continue with the rest of the presentation. Byron?
Thank you, David. So next we're going to be talking about string fuses. So string fuses, what is the structure of the string fuse? So it's got a housing which consists of two metal contacts with an insulator. Next is the fuse wire. So this is responsible for triggering of that fuse itself, which is normally centered in the middle of the fuse, as well as the cord sand. So this is for the termination of any electrical arc that happens. What is the function of a fuse? So the fuse is used to help with the overload and short circuit protection. So this is when the fuse wire physically melts inside the fuse itself and which breaks the connection point. So it's also due to the occurrence of electrical arcs itself. So string fuse categories. So you get part range protection, or AR, which is application for typically for short circuit currents. This is, however, not to be used with PV systems, as it has a much not as great turn of current. So that means it has a greater undefined unsafe section of current that can occur in that fuse itself. Next is your full range protection, or GR. So this is applications where it's suitable for short circuit as well as overload currents. So this is when it has a much greater turn of current itself and a much less undefined safe current compared to the nominal current that the system is currently running with. So this ensures that if it has reached that safe current, anything above that, it will automatically switch itself off in a sense. So what is full range protection? So as mentioned, it is GR rated fuses. So this is in accordance to the IEC standards. So only GR fuses are to be used with PV systems. And you would notice that some of the fuses are given a name of GR or PGPV with the following sign to represent the fuse itself. So again, it's exactly the same as what I've mentioned previously about GR fuses, where it has a much greater turn of current and a much less safe defined space, so that anything above said safe space, it is then classified as a turn off current to protect your system itself. Next is string fuses reactions. So this is the average current time curve. So this is the turn off time. So this will be your fuse time plus your arc termination time. So for the example that we're using here, we've got a normal current of 1 amp and we've got an overload current of 3 amps. So that means that our turn off time will be 8 milliseconds if we follow our graph for 1 amp and then an overload of 3. It gives us a turn off time of 8 milliseconds. So string fuse calculations. So this is where you'll then use the nominal voltage. U can be calculated as the U, so the normal, and then the UDC max of the inverter. So your nominal must always be greater than the UDC max of the inverter. So more precisely, the nominal voltage of the entire system must be greater at lower temperatures. So if you're installing a system that's going to experience temperature ranges lower than expected, then your voltages will be exponentially a lot higher. For nominal current calculations, so IN in this sense, so its derating factors have to be considered with it. So you got 4 derating factors that influence fuse characteristics. So you get alternating load factors. So this is when you've got a static factor for PV is normally 0.9. Also get an interrupting factor. So this is static and defined by the manufacturer itself, as well as temperature derating factor. So this can be either dynamic or mentioned in the datasheet itself. And then as well as fuse arrangements. So this is dynamic and depending on the number of fuse holders side by side. So for example, for string control, fuse factor of 1, and this will then also average your current time curve itself. Next, we're talking about is reverse polarities. So reverse polarity can cause damage or fire at the termination point where you are terminating your DC connections. String fuses help prevent this problem by acting fast. So your nominal current of the fuse should be not higher than the nominal closed circuit current, and this will then allow the fuse will not be then triggered, whereas the nominal fuse voltage should be higher than the string voltage for arc terminations. So for example, here we can see that we have a nominal voltage of 350 per string itself. So we've got 1, 2, 3, 4, 5 strings, and we've got a fuse here that is of 12 amp 900 volt rated, and we can see it on the positive side, and then our negative terminations are coming into the inverter. So with correct installation, you won't have reverse polarity in a sense. So this is how typically a normal installation will be done. If you have reverse polarity of strings with the installation of a 3 amp reverse polarity of a single string, the fuse will not trigger, and this is due to the amperage being too low to trigger. Whereas the installation of a 3.5 amp reverse polarity of the single string, this will then allows the fuse trigger to trigger, and that's correctly demonstrated, dimensioned. So here we can see we have a U nominal voltage of 510, and we've got a fuse rating of 12 amps, 900 volt. And because we are doing reverse polarity, so we've either got two positives in this sense, which means we've got a voltage of 1020 volt, which then will cause that fuse to then pop. Next section we will cover is AC grid system protection. So what is grid and system protection? So this is a protective device which constantly monitors the voltage and frequency of the grid for specified switch off conditions. So if, for example, if you have a frequency that is greater than what's determined, you can have that as a protection device to then switch off, as well as for voltages. So this is normally the GS protection. This connects the PV system, acts as a fail-safe by acting on the interface switch itself on the inverters, as well as the interface switch usually consists of an electrical switch gear connected in series on the inverters itself. So the variants for grid and system protection. So you got the normative requirements for grid and system protection differ from country to country, as well as for grid operators. So also sometimes require different versions or settings with regards to the requirements for grid protection. Basically, there are three variants for GS protection. So the grid system protection. So two electrical switch gears connected in series, for example. So the different variants, this is inverter integrated GS protection. So this is GS protection that is integrated in every typical inverter itself on the market today. So for PV systems up to a certain capacity, for example, in Germany up to 30 kVA, it has to be integrated protection, which acts on the integrated interface switch can be used. External GS protection is not required in a sense because the inverter is then responsible for that grid safety protection. The second variant is centrally realized grid and system protection relay and interface switch. So from a certain plant size, so in Germany, for example, a system greater than 30 kilowatt and less than 135, a central GS protection must be implemented. One way to comply with the standard is a central GS protection relay, which acts on a central interface switch. Both components must be installed, so you addition either externally. The third variant is your central grid and system protection relay controls, inverter integrated interface switch. So the second possibility for compliance with the standard is a central GS protection relay, which acts on the interface switch integrated into the inverter itself. So this allows for no additional interface switch has to be installed in the system itself. So you rely on the internal to act as the central GS protection relay. So how does it work with Fronius inverters? So on our conventional inverters, we've got our Fronius, Simon, and Eco inverters, as David has touched on, that have a secondary surge protection that can be installed. But for our power class from 10 to 27 on our three-phase inverters, you'll then have a controlled via a input. And then on our Fronius Gen 24 series, so this is from our 6 kilowatt to 10 kilowatt variant, it'll be controlled by WSD or wide shutdown protocol. And then it's the same on our Fronius Taro devices. So the 50 and 100 kilowatt variant is also controlled via a WSD, wide shutdown protocol. This is due to the Gen 24 and the Taro having shared the pilot card, and the Snap Inverter series has a data manager for it. So this is an example of a Bender GS protection with the Eco inverters. So here you'll have your Eco inverter itself. Here you'll have your signaling outputs. So here you'll have it connected to a relay with a normally open contactor, which is then fed by a power supply with buffering. So you've got a 240 volt, 24 volt DC relay that is then being operated by the inverter itself. If you are doing a GS protection with a Gen 24 and Eco inverter, so here you'll utilize the Gen 24's WSD function, so the wide shutdown protocol. So you'll have on the input, it'll then go to its own 24 volt relay. And then from the Eco 27, it will then wire into its own 24 volt relay, normally open relays. If you are doing GS protection with two Gen 24s or multiple Taro devices, it will then be wired as a WSD master and the slave unit. So you'll have a master with an in going into the control unit that has to do the GS protection. Here you'll also do from the output, it'll then have to the input of the slave unit that you are using. So for the installation of grid and system protection, there are typical requirements. So it's always important to observe the national regulations for the selection of the GS protection components. Again, this varies from national to regular requirements that are needed. So if you are doing an installation in Southern Africa, it'll be different to Northern Africa, for example. It'll always depend on national regulations. Always clarify the admissible with your grid operator beforehand. So always consult your grid operator before you are doing an installation on what exactly is required in terms of the system protection. If you is an external GS that is needed, it'll always be communicated. Next important note is the requirements for the relays. The relays must be installed in the inverter or nearby. If the relay is installed in the inverter, only in the Snap Inverter series, it must have a maximum width of the top head rail of 110 mils, a depth of 66, and then a maximum ambient temperature of up to 70 degrees, as the relay is mounted internally on the inverter itself. For the cabling and commissioning of the Snap inverters, Here's where you'll have your relay installed in the inverter itself, and then your input signals. You'll then have a signal that will then be coming out of the inverter, and it will then mount at the bottom of the reservoir card. It is marked out. Then you'll go into the Snap Inverters menu itself. So you'll enter the access code 22742. From here, you'll then have to tell it that the input signal, so the function of the existing signal, is off. And then you'll then have to set a triggering for it. So for the warning of the inverter to be shown. So for example, to stop the inverter switch is off, and also to communicate what connection type is then being used on that relay. So if it's a normally closed contact or it's a normally open contact relay. The next is the GS protection cabling that you would do typically on a Gen 24 Taro series inverter. So here's where you'll have your 4-pin plug, so you double your wired shutdown device inputs. And then instead of the bridge, so it's normally closed, you'll then have your GS protection internal is then potential free contacts is wired into your WSD. So this allows for no special configuration is required on the Gen 24 Taro units, just to make sure that you do enable the WS, the wired shutdown devices are enabled on the pilot card itself. So here you'll just use a normal Cat5 cable to set pair from your GS protection to your WSD on the Gen 24 Taro series. So if you are doing your GS protection with multiple devices, again, you'll need to enable on the master card that it is on, for example, from the GS protection, and then your following cards will be set to off or 0 in a sense. You'll then use again a cat cable twisted pair to then communicate that signal through the multiple inverters in a sense. So the parallel use of an SPD and the GS protection. So this is when you're using the integrated SPD, so the over voltage protection type that David has touched on. So the in typical example that we are using is type 1 plus 2. So this is where it will normally change. So your GS protection contact, so this is from your WSD itself, and then your integrated SPD will then be wired directly into the V+, and then your internal IO for pin 8. The triggering of the SPD will lead to feed-in limitation. So you'll have a state code 103 is normally displayed on your SolarWeb app. The WSD warning error message is displayed as error code 130. So this shows you that a wired shutdown has been triggered and the inverter has switched off. For this, you'll then have to make use of the web interface for the Taro and Gen 24 for the IO control settings. So here we can then set the feed-in limitation settings. So if it's 99%, this means only 1% limitation, which will give a warning. 0%, which is then a 0 feed-in, so it's a warning plus the inverter will stop. And this can be found under the IO power management tab on the inverter itself under the commissioning. Important to make note is we're using pin 8, as mentioned before, where the SPD has been plugged into. For further information, please see is our supported regions for each TSA or technical sales advisor. So for David Mange and for Cyprian Okulu, and as well as myself, these are the areas that we are supporting. Also important to make note of is our Fronius System Partner Plus. So these are our local sales partners that are normally located. They are your level 1 of support and also stock replacement parts for Fronius inverters. Recordings are available for previous webinars on our homepage, as well as operating and installation instruction manuals. can be found at Fronius downloads, and as well as on our YouTube channel. We've got our how-to and installation videos, as well as webinar recordings, and a dedicated Sub-Sahara Africa playlist. For further information regarding technical questions, trainings, sales international, and after-sales service, please contact the relevant email addresses. And for the TSAs itself, our contacts are down at the bottom for you to be able to contact us. Thank you very much for attending today's webinar.